Now, we unfortunately, we are limited to 9 hours.
Oh, thank you very much. I don't see any sandwiches. I don't think I can last for 9 hours. Okay. My name is Herb Reiter. I am president of EDA to ASIC Consulting. I started this business exactly 10 years ago to bridge the gap between EDA design environments and the ASIC or semiconductor business in general. And I enjoy what I'm doing because all my projects, all my efforts are focused on very smart people, creative people who are really driving our industry forward. Anyway, Steve Liebsen asked me to talk about my history, how I got into 3D. And before talking about 3D, let me give you some more of my background. I started my marketing roles long time ago in the 80s at National Semiconductor in Europe, and worked as one of my first projects on programmable logic. This was a brand new product and nobody really understood how it works, nor understood the potential of this technology. So I was my own marketing guy, my own field applications engineer, my own debug engineer, and I had a programmer under my arm whenever I went to a customer to capture their logic circuitry into one of these PLDs. Maximum complexity was about 50 gates at that time, so you can guess how long ago this was, and solved their board space problems. This was the biggest plus for PLDs at the beginning, because they could replace 5, 6, maybe 10 logic devices and reduce board space. And while the component cost was much higher than the component cost of the parts such a PLD replaced, it was compelling because it reduced the board space, board cost, and of course system cost as well. After I worked on PLDs for a few years, I changed to National Semiconductor in the US and joined the ASIC division. And in the ASIC efforts in the mid-80s, it was also a very much of a pioneering effort, because people were used to enjoying 7400 logic parts or CD4000 CMOS equivalents and so on. And nobody was willing to wait 6 months or a year to implement a function in an ASIC device, because it was much easier to buy components off the shelf and put them together on a board. But after several years on pushing bipolar gate arrays and then CMOS gate arrays and eventually CMOS standard cell technology, people captured the benefits and understood the benefits, but National Semiconductor as a commodity house had a very hard time doing 2 wafers as a run for a certain prototype, so National couldn't succeed in this area, so I changed to VLSI technology. And VLSI technology at that time was the #1 ASIC vendor in regards to really complex cell-based designs.
What year was that?
This was in 1989, after the big earthquake. So the big earthquake made me make a big move. And anyway, it was a real pleasure to work at VLSI technology in the early years, in the late 80s, early 90s, because VLSI was clearly the leader. They had a very good process technology, and most importantly, they had their own in-house tools. So they had a fantastic design flow for cell-based, and many customers told us at this late 80s or early 90s visits, you guys have to come through, don't tell purchasing that we don't have another choice, but you have to come through with this device, packing all kinds of functionality into one chip. However, as some of you may remember, VLSI technology tried to split off the software side of the house and basically starved it by not funding it enough internally and by disabling a lot of customer contacts the Compass people were trying to make, because this Compass software would have made the competition stronger. So VLSI tried to have their cake and eat it too, which was of course very limiting and went to basically a severe decline, and frustrated me and my engineering colleagues, because we had on 100,000 gates 10,000 unroutes. So that's no future. So that was my motivator to change my career from the semiconductor side to the EDA side. So I went to ViewLogic and became ViewLogic's semiconductor vendor alliance manager. So we worked with the big semiconductor vendors, big ASIC vendors at that time, in the US, in Europe and Japan, and integrated the ViewLogic tools, VCS, dynamic simulation, Motif at that time, static timing analysis, and also test gen and ATPG tool into the design flows. ATPG test gen was not very successful, but VCS was reasonably successful, and the real kind of killer tool turned out to be Motif, because at that time the transition from quarter micron to 0.18 or 0.35 quarter micron and 0.18 was in full swing, and as you know, the simulation times increase exponentially with the gate count. And as the ASIC chips got larger and larger, you had simulation times not of hours but weeks and multiple weeks. So the industry was really screaming for a better way of doing timing analysis, because timing closure at that point was a major headache for people. And as you know, dynamic simulation is also not exhaustive, versus timing analysis, static timing analysis is. So if you did simulation for weeks, you were still not sure if you had eliminated every potential timing bug. With prime time, with Motif at that point, you clearly were sure.
Getting ahead of yourself.
I'm getting ahead of myself, and you're right, because my stay at, my tenure at ViewLogic was kind of shortened, because shareholders of Synopsys decided about a year after I joined ViewLogic to invest $400 million and buy ViewLogic. And this was at a very opportune time, because we had exactly a static timing analysis seminar with a lot of customers, and it was a 2-day session, and on the first day we told them about Motif and belittled a tool that was competing with Motif called PrimeTime that Synopsys was introducing. And on the evening of the first day, where we convinced everybody that Motif was the way to go, we got the announcement that we no longer were ViewLogic, but we had to now turn in our ViewLogic badges and get Synopsys badges. So in the morning of the second seminar day, there was first a big smile for about 10 minutes on everybody's face, and then we changed our message from use Motif, buy Motif, to use Motif, by use PrimeTime, buy PrimeTime. I also worked on VCS, continued, but of course test gen from ViewLogic disappeared. And that's just 2 examples, programmable logic in Europe and ASICs, ASIC tools, ASICs at National Semiconductor and then at VLSI, and then ASIC design tools that I love to introduce new products. I seem to enjoy being on the bleeding edge of technology.
So how did you get involved in 3D?
And now the big question is, why am I in 3D? I read about 4, maybe almost 5 years ago, an article that Matt Nowak and Rajko Radojic from Qualcomm wrote, promoting stacking die and combining them in one package. And this was a very compelling message. This was a great idea in my mind. And so I was at that time managing the ASIC working group at the GSA, and the EDA working group at the GSA, and where we tried to identify new EDA requirements for our industry and hopefully preempt divergence in regards to interfaces and simplify standards efforts. And at that time I said, no, EDA is really not the priority. I felt that driving 3D efforts was more important. So in summer of 2008, I redirected the EDA working group into a 3D working group. And that's what I did on behalf of the GSA team in dollars to educate the industry about the potential of 3D technology and not so much about the challenges we had to face as 3D became more and more interesting for more and more people. And as you may remember, 2-3 years ago, 3D technology looked like a panacea for any kind of problem the semiconductor industry ever had or ever will have. And you may smile because this is really not true. 3D has its own challenges, and one reaction of our industry to these 3D challenges was several years ago already the introduction of 2.5D. And 2.5D is not stacking die vertically, but arranging die on an interposer. And this, of course, reduces the amount of challenges, at least for high power dissipation designs, because it's much easier to cool a number of die that are arranged side by side, kind of wrench style, instead of having a skyscraper of die on top of each other, one die heating up the next one and leading to reliability problems and eventual total failure. Okay, let me look at this cheat sheet. What else? I think I have answered the question about how did I get into 3D. Let's look at the next point here, state of 3D readiness today as I see it. Up front, a comment, when I say 3D, I also mean 2.5D, because my personal opinion and an opinion shared with many experts in this business is that certain applications are much better served with 2.5D, not just today, but for some many years to come, versus other applications will be better served with 3D. So I clearly believe these are parallel approaches to applications that can be best served with one or the other technology.
I agree. I really don't like discussions about how 2.5D is not true 3D. They're both engineering solutions.
I'm really concerned that some people belittle 2.5D. I do understand that 2.5D is of course not as cost effective as 3D will be, and people who are really cranking out millions of units will try and continue to try to go to 3D. However, if you have a 2.5D solution, you typically have less time to market, and unless you have a high volume, you also benefit from a lower overall cost, because I see NREs for 2.5D being less pricey today or in future than 3D, because 3D has much more design effort involved than 2.5D. And as I said before, power dissipation is today a major concern for stacking die in a 3D vertical configuration.
So I want to talk about business issues, because you were more concerned about those than even the technical issues yesterday.
That's another point that's really important in my mind. I know our industry for more than 40 years. And I have seen always good engineers providing solutions. They may not have been the most cost-effective solutions at the beginning, but with cost reduction efforts, they always became viable efforts. And I'm convinced that 3D, 2.5D will go the same way. That the engineering teams will figure out how to make this technology cost-effective. And when I say cost-effective, I don't mean lower cost than the components they might be replacing, but lower system cost, lower overall cost.
Yeah, not lowering the BOM cost necessarily,
right?
But lowering the overall system cost because of manufacturing cost differences.
Exactly. I have seen the same happening in programmable logic 30 years ago, 30 plus years ago, and in ASIC 20 plus years ago. And I'm convinced that 3D and 2.5D will go the same path. As economies of scale kick in, as predictability of yield gets really solid, you have a much better chance to make very cost-effective components, and in the overall system context save significant amounts of money. Where is 3D today? As I just talked about the engineering perspective of 3D, I want to bring up my next very important point, which is the management perspective of 3D. When I worked at National Semiconductor in the 80s on programmable logic, all I needed to build an ecosystem was a little bit of software that converted Boolean algebra into a bit matrix for the programmable logic and the programmer. And both capabilities were available at Data.io and various other companies. So I had a very simple ecosystem, National Semiconductor and Data.io, and we were off and running. On the ASIC side at National Semiconductor and at VLSI, I saw already that two companies would not get their arms around this technology. There was a lot of subcontracting already going on in regards to packaging. The foundry business was emerging at that time as a very cost-effective way of generating manufacturing silicon compared to manufacturing it in your own company. Of course, software was coming in addition to internal sources from the outside. Mentor at that time was very dominant. And clearly the ecosystem was much more complex. Also, as the ASIC components were more and more complex, more and more gates packed into one package, the system knowledge became very important. It was not just assembling a bunch of gates, it had to be really having a high impact on the system level, following the right standards, defining the right interfaces to the rest of the system, and these components, these considerations were of course requiring expertise from system houses. These guys were pulled into the ecosystem, and why am I telling you this kind of stuff? Because 3D is another step up. You need a much more complex ecosystem to really succeed, and succeed cost effectively with reliable solutions. And as I showed yesterday in one of these slides, you have many more considerations, technical and business considerations, to be aware of, to put on the table as you're making decisions. And the important thing, I think, for our industry is, for the success of 3D, that management of companies that focus on a piece of this ecosystem need to be very open-minded in regards to working with others in this industry to really make cost-effective solutions possible and minimize the risk in regards to working together.
And one thing you pointed out yesterday is that we saw this before in the migration from IDM to fabless.
Oh yeah, that's an important point as well. Thanks, Steve. as you may remember, when the IDM business model became less cost effective, the foundries really established themselves as very credible sources of silicon, and the OSATs, the overseas assembly and test houses, became very important in this ecosystem to bring the cost down. And just like the automotive industry, where you have a lot of subcontractors that provide their components to an assembly house that builds the entire cars or trucks, we have to learn as a semiconductor industry to behave in a similar way. There will be companies emerging who are really good in power management solutions. They will eventually provide on a die, a bare die, a known good die as we call it today, a solution to add into the stack and do a lot of this power management. And if I may emphasize, compared to today's IP business, this die level IP business will eliminate a major headache we have today with soft IP, or even more with hard IP, because if an IP block gets developed for a particular process technology, and the fabs always improve their process technology, this IP block imported into a customer's design, and then the design manufactured on a different process technology, even if it's only slightly different, can cause problems. Versus if you have a die level business, you can manufacture a die bank with a known good die, and nobody cares when you assemble 3D stacks what process technology has been used. If this was an analog process or a memory process or a logic process, if it was 90 nanometer or 20 nanometer or 130 nanometer, or bulk silicon or SOI or silicon germanium or whatever. So it gives us a lot of flexibility to really implement every system function in the right process technology, cost effectively, and most importantly, power efficient.
So this is a return back to the future, because that's what we used to do with board level design. We didn't care what was in the chips, they just all went down on the board.
Exactly, that's absolutely the case. However, if you look at the technical specs that are possible in this direction, you will have systems in future consuming 10 or 20% of the power dissipation compared to implementing on the board level, and in addition they will get faster, because as you're reducing the interconnects, you can offer much higher performance at lower power. And when I give presentations, I have many times system people jumping up somewhere and saying, "Are you trying to tell me that I can make my next generation system with half the power, twice the speed?" And I can say yes. And here again, a quick plug for 2.5D technology. 3D technology, die stacking in a vertical way, is of course very compelling for identical memory die, because all the pinout, all the data lines, clock lines, power supply lines are basically standardized by definition. If you are stacking vertically heterogeneous die, you have to have standards in place. And that's a weakness of today's 3D ecosystem. We have a very limited amount of standards in place, and so that's a reason why heterogeneous die stacking vertically will take some more years to come until the standards are in place to make these components, these die level IP components, work together.
They're really awaiting bus standards that we used to have to deal with in the 70s, like the S100 bus or the multi-bus, to allow boards from different manufacturers to plug into a system. You had to standardize on the physical connector and the signals. It's the same sort of thing that's required for heterogeneous die stacking.
Right, right. So I love to hear your comments because you have system level experience. And so we are integrating an entire system into a package. It shouldn't be called 3D ICs. It should be called 3D systems implemented in an IC.
Okay.
Or 2.5. Okay.
So where is it going?
Where is it going? I see already significant efforts in our industry to take standards seriously. If you look at the wide I/O standard, for example, that's a standard that was driven by a number of cell phone vendors and tablet producers because it clearly reduces the power dissipation of a certain function like HD video playing can be reduced by about 50% in regards to power dissipation compared to LP DDR2 standard today, which means you can watch 2 HD videos with 1 battery charge instead of 1. So you can go to work and sit in the train, watch 1 video, in the evening going home you can watch another video. That's clearly a user benefit, and I'm sure the consumers who are driving today's semiconductor industry, I learned that about 55% of the semiconductor revenue comes from the consumer segment, not like years ago where the computer segment was dominant. So that power dissipation is a big value for the end product. If it goes to the consumer, equally important, if you talk to a data center manager about selling him a new server, many times you may find that he looks at you and says, I can't afford this new server because I'm maxed out in regards to power dissipation in the data center and cooling capacity of my infrastructure. If I buy this additional server, I have to build a new building. So coming up with servers that suddenly consume half the power or even less will be an enormous value proposition for the data centers as well. And I'm sure you know Google and various other companies have huge data centers and huge electricity bills. So if we can reduce these electricity bills and simplify the cooling challenges, that's clearly a value proposition that will help our semiconductor industry to grow. I would like to emphasize again that industry organizations like Sematech in Albany, like IMEC, like LETI, like ITRI, and many others have to be taken very, very seriously, because unless we can agree either point to point or within these industry organizations on how to work together, we will have enormous cost disadvantages and enormous risk elements on the table that we can eliminate very simply by talking to each other beforehand. And as I said at the beginning, the challenge is that MBA trainings so far have not talked a lot about cooperation, and our business managers and our executives are much more trimmed and motivated towards competing versus collaborating with somebody who might be a horizontal competitor or argue with you in regards to vertical competition, who takes how much of the food chain and creates how much value and takes how much margin. So that's my main concern for the success of 3D.
Okay.
And again, automotive industry has demonstrated that building an ecosystem and working together and really having sub-assemblies and component suppliers deliver to a central point of assembling a car is very cost effective, because I remember the first Ford cars were about 1 annual salary of a worker. Today, nobody would buy a car in exchange for an annual salary. So that's a perfect example how cost effective and how good quality and how versatile this principle of cooperation, of ecosystem cooperation, can really